Welcome everyone to another episode of Flyover Live. We're coming to you from Liberty Street on Mass Ave in downtown Indianapolis. Let's get started. Thank you all for joining us for this week's episode of Flyover Live, a weekly podcast talking about the latest sports, entertainment, political news from the eyes of three Midwestern millennials. I'm your host, Cliff Dennis, and I'm joined today with Mark, and
Hey,
Brent is out today.
gonna have to try and pick up the slack.
Yeah, he's out working
not
hard.
optimistic.
Before we get started, I wanted to make sure everyone knows to check us out on Instagram and Twitter. Both of those handles are at FlyoverLive, and on Facebook at facebook.com/FlyoverLive. Well, we are totally nerding out today. We have an all-science episode of Flyover Live for you, so get ready. Hold on to your butts, because our guest today is Professor of Physics and Astronomy Brian Murphy from Butler. And in honor of our guest, for those of you watching on YouTube, I have to just say that I wore my professional tweed professorial jacket today.
And I didn't.
I know, I was telling Mark before we started the show, I was like, there's a good chance I think I'm going to look more like a professor than our
Yes,
guest
you do.
today, but I just had it in the closet and thought I'd whip it out today. So it's a good looking.
I thought it was lawyer garb, but
No, I was thinking of professor. So, but anyway, enough about my jacket.
all right.
But so Brian graduated from University of Iowa with a Bachelor of Science in Physics and Astronomy, and from IU with a Master's in Astronomy.
Master's and PhD.
And PhD in Astrophysics from IU, yeah. And then you currently are the professor at Butler, director of the Holcomb Observatory,
Right.
and department head for physics and astronomy.
I
right?
was department
What?
head.
Okay.
And decided I wanted to go back to doing research and teaching.
Okay.
So I got out of administration a few years ago.
So more time to research and
Right. A department head is
dive
sort of
into things.
department heads are glorified titles in academics. It means you're just piling on, doing a lot of paperwork versus
I see.
what you really got into the field for.
I see. And then I was looking through your history and everything. So, senior fellow at Cambridge.
Yeah.
So you spent
A summer in Cambridge. I was numerous places, and typically the way it works in academia, particularly in the sciences, after you get your PhD, you do what is called 1 or 2 postdocs, where you work with other people who are well established in the field. And that's
Sure.
mainly to build up your networking and publication record, so you can try to get a faculty job, which are far and few between. The faculty jobs are the primo positions to have, particularly in astronomy, because they can become permanent positions.
I see. And so, any huge takeaways from your time in England?
I actually loved it. I had a tiny little flat, as they call it in England, and it was only 1 block to the center of town where all the markets were.
Okay.
And so in Cambridge, England is just a beautiful town. But it was nice walking around the campus and you see, oh, here's where Isaac Newton taught.
Oh, wow.
And things like
no
that.
big deal.
Yeah, big deal, so.
That's where Isaac was.
Yeah, Sir Isaac Newton, and you meet a lot of other people at the Institute who also have the title of Sir. Of course, you don't necessarily address them as that if it's in sort of just over coffee.
And not to get super pop culturally here, but A Beautiful Mind, was that
He was
Cambridge?
actually at Princeton, I believe.
Princeton.
Princeton,
okay.
yeah.
I was just thinking I'm just imagining folks in those fancy like robes wandering
Right,
around.
and some universities still have that today, particularly for their dinners and stuff. They have to
Okay.
wear their garb. We at Butler are less formal than that, and once a year I bring out my academic garb for commencement. So
But at Cambridge, none of that. They dress
sometimes
down.
they do bring their garb out for dinner too.
Oh, okay.
Yeah, so there is, in certain schools.
Kind of a cross between Harry Potter and
Right,
graduation.
Right. And I have the Harry Potter garb sitting in my closet at home, so
Well, yeah. Well, we've got Halloween right around the corner, so
I could dress up as a professor.
there you go.
Cliff did today.
Apparently, it's what I was going for. Well, anyway, might as well jump right into some topics that I was really interested to talk to you about. The first is a recent discovery.
This, by the way, has been probably the most excited Cliff's been for a show because he finally has somebody that he can talk intelligently about this stuff with. Like,
Yeah.
he'll try to explain to me some of this stuff, and my eyes just kind of glaze over because I don't understand what he's talking about. So this is a big one.
When you talk about things that people nerd out on that they don't really have any business sitting around reading articles about. This is my area. So
Yeah, it's very interesting. I just can't keep up.
while you guys are discussing football, I'm reading articles about exoplanets. Speaking of, the Kepler mission, for those people listening that don't know anything about the Kepler mission, and I guess before I dive into a specific, recent discovery, tell folks what that's all about.
Sure. Kepler mission is basically one of the ways we can find these exoplanets, and exoplanets are planets outside our solar system orbiting other stars. What its purpose was to do was to look for planets passing in front of their parent star. And by passing in front of their parent star, it means they would dim ever so slightly. And as an example, imagine a pea passing in front of a beach ball-sized star. That would be the Earth passing in front of the sun. It might dim by a fraction of a percent, but that's measurable. To do that, though, to measure something like an Earth-like planet, you have to go into space to do that. And what the Kepler mission did for 3.5 years was stare at a single part of the sky 24/7 for 3.5 years straight and look for stars that were dimming. So it was following 200,000 stars to see if there's any periodic dimming. That is, if something's orbiting around the star, you would see it dim as the planet passed in front of it, then again, and again with an exact period. And that's how they would determine whether they found a planet.
And it was for about 3.5, 4 years, and then recently there was some trouble with the mission, right?
Right. It lost some of its gyroscope, so it couldn't point very accurately. And so they revised the mission to just look at sections for a month at a time now, to look for other types of planets. But the Kepler mission is curious also in the fact that from just the observations it did, it's discovered close to 2,000 planets, which is really amazing considering it's grown exponentially just in the last 6 years or so, the field.
Sure. Because prior to the Kepler mission, I mean, we were talking about a couple hundred stars.
Right, couple hundred
planets.
maximum planets.
And that's most likely just because of the advancements in technology.
Partly the advancements in technology, but also just search mechanisms and algorithms to go through the data. That's a big one. And frankly, the topic you're about to talk to, I'll give you an interesting little tidbit about that too.
Okay. Well, the topic is that that in looking through the data, the Kepler mission has opened up after a given period of time. I don't actually recall the amount of time. They opened up the data to everyone, and so there's a planethunters.org, I guess, a citizens-based. Anybody
what we call
can go,
citizen science. Basically.
Right. Anyone can log in and go through the Kepler data. They try to kind of make a program, I guess, so that people can, in an easy way, try to help scientists track dips in the starlight so that they can see if there's a planet there. But through that process, found a very mysterious star, not necessarily anything about exoplanet, but just a weird dip in starlight. And so this Kepler star, which it has a real sexy name.
Yeah, I can't remember the name. It's what is it? K something 8. It has an 8, a 5. It has almost every number of the 1 through 10, I believe.
Right. So they're not. And this is an issue with the planets they've discovered too, is that no one's naming these planets that they've been
There's
discovering.
just so many of them. That's the problem.
Yeah, but KIC 8462852.
Oh yeah.
That one, that
one,
star. Yeah.
Right.
So
course.
anyway, everyone's trying to kind of tamp down the speculation, but these weird dips in starlight, could be a number of things. But if you want to take it from there, I think the biggest one that people are excited about is that if it was some kind of megastructure that
Right, and not here on Earth, an alien megastructure.
Right.
So, well, the key thing about it, how it was found was interesting because it was one of these citizen science projects. Kepler has algorithms that looks for those periodic dips we just discussed. If it's periodic, it means you have a precise orbital period around the star, and you see the dimming of that. And typically these dips can be anywhere from a tiny fraction of a percent to maybe a couple percent. And if it's a non-periodic dip, what can happen is the Kepler algorithms generally don't catch that because it's non-periodic. And it's probably an eclipsing binary or something like that, which may have some periodicity, but it would be much larger than a few percent.
Which that would be two stars?
Two stars orbiting
each other?
close to each other. You would have one comparable size, so you'd see a comparable, fairly sizable dip of maybe 50% in the brightness. Planets only cause a tiny dip because they're relatively small.
Sure.
Jupiter, for instance, which is the largest planet in our solar system, if you were looking at it from a distant star and it passed in front of our sun, it'd just be a 1% drop in the brightness of the sun. And Jupiter is about as big as you can get as a planet in terms of radius. And so this thing here dropped over 20% for a day or so, and that was it. And then it was a number of drops of varying magnitude, and they were totally non-periodic, whereas in the paper they said aperiodic. And so none of the algorithms caught that, but the Citizen Science Project, they found that people could go through and look at 30, I believe it was 30-hour segments of data. And in those segments of data, the human eye could pick out 85% accuracy of what was a planet and what was not. And so with one of these, they caught these dips, which were totally non-exoplanet-like.
Right.
And we're wondering, what's the structure then? And so I did read the paper before coming down here, other than just press articles, because press articles can lead you astray.
Right.
And so I wanted to hear read what the scientists said. And I didn't exactly find anything where alien was in there. But that was speculative. But the thing is, it's such a large dip, and looks like some sort of, well, who knows what at this point, that could be obscuring the star.
Sure. And I think some of the more boring explanations that I think I may have ventured into the paper that you're referring to in my own time, and probably I think all I did was read the number of summaries that were in the paper. I'm obviously not looking through the
Typically,
science.
a scientist goes to the abstract and goes right to the conclusions.
And so it looked like the more boring explanations were clouds of dust or comets or asteroids
swarms.
So
there was one sort of the Aldebaran thing where a planet collided with another, and you had planet fragments too. But that would probably produce some sort of periodic fashionable thing too, where you see this swarm of debris come around the star, and we didn't see that. So that's where the comet swarm was coming into play.
Well, and then what I read today was just in case SETI has turned its radio telescopes to...
That is certainly correct. The SETI, the Allen Array Telescope in California, is now looking at this, because you never know. I mean, we've had things before dating back 40, 50 years. For instance, the first discovery of there's a discovery back in, I believe it was 1966 or 1967 at Cambridge. All right.
Is that the WOW signal?
No, that was actually through Ohio State, I believe. This is a young graduate student named Jocelyn Bell, was working for Anthony Hewish, who now has a Nobel Prize for this discovery. They were actually just looking at the sky, doing a survey. And survey work is among the most boring kind of work you can do. You just scan for sources in the sky. And you're just, okay, found something, Okay, another object here, another object there. You give the coordinates. Well, Jocelyn Bell had come up with this thing that actually showed that she had this pulse that was going beep, 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 more precise than any clock here on Earth, 33 times a second. And so she brought it to her advisor, Anthony Hewish, and he looked at it and said, well, it's probably noise from some washing machine or tractor off in the distance, emitting some electromagnetic energy. So the next day she's out again, sort of scanning the same area in the sky with the radio telescope, and saw the same beep, 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 but it was 4 minutes earlier. Then the next day it was another 4 minutes earlier, and the next day another 4 minutes earlier. And that there indicates that it was extraterrestrial. And by extraterrestrial, we do not mean life. We mean it's not here on Earth, because it's doing sidereal time, which is rotation period of the Earth, which is 23 hours, 56 minutes, which is sky time. And they labeled the signal LGM, and they kept quiet about it for the longest time because they wanted to figure out what it was. LGM stood for Little Green Men. So because they were anything they thought it was perhaps one of the things they said, well, maybe it's a beacon, so let's just keep it quiet.
Yeah.
It wasn't a conspiracy, but we don't want anyone to steal our thunder here. And so they looked at all the possibilities, and they said, well, is it a rotating star, a pulsating star? And it turned out that No, it was a pulsar about the size of Indianapolis. It fit inside 465, but the mass of the sun, 300,000 times the mass of the Earth.
Wow.
And that was the first discovery of a neutron star, which won Anthony Hewish the Nobel Prize, because he was the one who figured it out, explained the observation. So this observation is very similar to that. We don't know what it is at this point. Could it be perhaps an alien megastructure? Yes, it could be. But the likelihood of that is probably not. But if it is, it's spectacular.
So if anybody wants just like a free Nobel Prize, all they have to do is figure out what this is, and they probably get it.
Right. It's not just doing an observation for a Nobel Prize, it's figuring it out too. Because anyone can have a chance discovery, but if they don't know what it is, it's just pure chance.
Speculation.
For all those people out there that are looking for Nobel Prizes,
join that citizen science group with Kepler.
Well, and I think I read that it's 1,400 light years away, so any chance at observing it in methods other than just light and maybe...
Right. They're actually going to look at spectra of this thing, too. And they have looked at some. They looked at for an infrared signature, would indicate whether there's a cloud of gas. And you mentioned the cloud of gas. It doesn't seem to have this infrared structure or signature in the spectra that would indicate there is a cloud of gas around it. So that's why they sort of ruled that one out. They put a cometary swarm heading toward it, because comets puff up and balloon up when they get near a star.
Sure.
And they thought, well, if there's a lot of them, that could perhaps cause this dimming.
So will there be a way for them to narrow those down?
Yeah, and I'm sure, given ingenious as most of the community astronomers I know, they're going to figure this out and come up with observations. And some of the larger telescopes are going to be pointing at this, trying to figure out what it is, because it's publicity.
Sure.
And everyone likes their name in the paper, so and a Nobel Prize is even better. So.
Right. Well, the other
other
discovery that Kepler recently had was back in July, Kepler 452b, and that was the first super Earth around in the habitable zone of a sun-like star. So, briefly, I think.
What's the super Earth and what's the habitable zone?
Right, I was going to say, I mean, these are all terms that I'm throwing out there that you never know.
These are all new terms because, as mentioning, prior to 1995, we only knew of, well, let's call it 8 planets, not including Pluto, okay? And that's because we knew of none out beyond our solar system. But since then, we're up to close to 3,000 planets, most of these via the Kepler spacecraft. And given the Kepler spacecraft, the number of planets it found, we now have statistics on what the most common types of planets are at least in our galaxy or nearby us. They appear to be what are called super-Earths and mini-Neptunes. And you might say, what's a super-Earth, what's a mini-Neptune? Which you have said at least half that question. So a super-Earth is a Earth that's, well, super. It's larger than Earth. But it's not outrageously large, say like Jupiter or Neptune. And then there are many Neptunes which be comparable size, but they're made of lower density, what we call hydrogen compounds, water, methane, and perhaps ammonia. Whereas a super-Earth would be made of more what the Earth is, silicates and iron and nickel. And we found a number of super-Earths. In fact, like I said, they seem to be the most common planets. Jupiters and Saturns tend not to be the most common types of planets.
But we're the first discovered just because of their ease in detection.
Right, the ease of detection. Imagine Jupiter passing in front of our sun. It's easy to detect that dim. We've done that from Holcomb Observatory, where we've seen Jupiter-like planets passing in front of stars. Not discovered them, but just observed the timing of them.
Just because they're the biggest?
They're the biggest, right. They're easy to, in fact, the first ones detected were 10 times closer to their parent star than Mercury is. And they're actually referred to as hot Jupiters. And that's the nice thing about astronomy, unlike, say, chemistry or other fields. The names we come up with, we're simple-minded people. Super Earth, hot Jupiter, mini Neptunes, black hole, red giant. It's all very easy terms, which I think that's why the public likes astronomy.
Just like the name of that planet, like the H8.
I'm sure someone's going to dub it something else, but there's actually contests out there that name planets with the International Astronomical Union now.
I think I saw that they called it Penny Star. I guess that was the astronomer who.
It's not official, but it has to go with the IAU. It'll probably get some other name, but we've run out of Roman Greco gods in our own solar system, so we're going to other things like other names now. But then a super Earth is something that's somewhat larger than the Earth, maybe up to twice the diameter. Comparable composition though, but it has to lie what's called the habitable zone to be a planet we could perhaps live on. Now, it can't be Mars size or Mercury size because they're no longer geologically active. and they would actually not have much of an atmosphere. So you need something Earth-sized or Venus-sized and larger in this narrow zone around a star. And by habitable zone, we mean a place where liquid water could exist that far from the sun or its star. If
Also
you're-
known as the Goldilocks zone.
Goldilocks zone, not too hot, not too cold. As if you're too hot, your water evaporates like Venus did, you get a runaway greenhouse effect. Too cold, everything freezes, you have no liquid water. And that, right now we believe liquid water is the key to life, so that's why we call it the habitable zone. And super Earths presumably would have these traits, that if they're in this zone, which we can determine how far they are from their suns. So that's why this one was interesting.
Sure.
Now the next thing is looking at, what the perhaps composition of the atmosphere is.
Trying to confirm that.
Right.
Because really all we're doing is observing these planets
the key,
by the light curve, not
right.
anything
The
more
interesting thing is,
specific.
yeah, you said light curve, we don't even see the planets. Probably 95 to 98% of these planets we have never seen. We just know they're present from their effects on their star. And
Which can be kind of deceiving because you see the news articles and there's some artist
right. When we can determine their size, we can determine their distance from their parent star. We can actually determine what their density is, which gives us their composition from the mass and the radius. And so that's the interesting thing we have going here with that is, and I try to tell people, you look at a star through a telescope, it's just a point of light. But what you can decipher from those photons traveling through hundreds of light years of space to our telescopes and into our instruments, and then having a human at this end deciphering it all is really amazing that you can do that.
And so is that kind of the next frontier in exoplanets, is trying to discern the elements that make up all these exoplanets?
Right, because we know some of these now are in the habitable zone. But then again, Mars technically is in the habitable zone too, but it's too small. It's geologically dead. But
Mercury is
Mercury is way too close to the sun. Venus is too close too, and the Earth is about 5% out from the too hot zone.
Okay.
So we're close to it. Another 5% inward, and we would be cooked just by a runaway greenhouse effect.
It's a little disconcerting.
Yeah, well, it's going to happen in about 1 to 2 billion years because the sun's slowly increasing its luminosity, even before it blows up into a red
So you got
giant.
that to look forward to.
Yeah.
Yep.
And you have to look at, the other thing is you have to look at what type of star it's orbiting. If it's a star that has a lifetime of 10 million years, you're not going to have life around it because it's too short a lifetime. You want a star that's going to last at least a few billion years. And that's where you get into a certain type of star, sun-like or slightly less massive.
And that's kind of what, with Kepler's new mission, K2, it's observing all red giants, which are those shorter lifespan stars, right?
Well,
Or not
red dwarfs.
Red dwarfs.
They're actually longer
life.
lived stars. And because of that, the premise there is, because they're red dwarfs, it means they put off a lot less luminosity than the sun, which means the habitable zone is very close, which means the planet has to be close in moving rapidly around it then, because it's so close. And because of that, it means you can observe multiple periods of these things. And also because the red dwarfs are small, an Earth-sized planet passing in front of it is easy to observe. It will have a much bigger effect than on a larger solar type star.
But the issue with those is that the planet's probably locked kind of like the moon is.
Right. And that's a good point. You get too close, you're tidally locked, and all your atmosphere is going to go from one side to the other and freeze out. And so the question is, what if there's a equivalent of a Jupiter close to one of these things? You can actually then have a satellite orbiting this, and I give an example of a science fiction movie, Pandora and Avatar.
Yeah.
Which was the same type of thing, where you had a Jovian Jupiter-like planet and a satellite which was orbiting around it, which meant that thing was more on a rotisserie versus one side being baked.
Sure.
So you could possibly have, if you're in the right zone area, have that.
So I think in all of the discussion about exoplanets, Kepler, everything is kind of, everyone gets excited about trying to discover the fact that there is water on these planets, if possible, with the and so one mission that's coming in the future is the James Webb Telescope, and that's the next generation of Hubble, right? So that launches soon.
Yeah, and it's interesting you bring it up because I have a slide when I talk about telescopes where I present the picture of the James Webb Telescope, and at the bottom it says to be launched in 2007. And I kept that slide in my lecture because it shows sometimes how slow progress goes.
Right.
The earliest, I think it's 2018 now is when it's going to be launched. And the thing is, it's going to be roughly, well, the Hubble is 2.4 meters in diameter, its mirror. And you can think of the mirror as the size of the pupil of the telescope. Imagine you had a pupil that big. You could see a lot of dim objects. The Webb telescope is going to be 8 meters across, which puts it near 25 feet across,
Wow.
which means it's going to see, we're talking much larger than the Hubble, on order of 3 times larger in diameter and have close to 10 times dimmer objects. But it's optimized for infrared for 2 reasons. One, so it can look at the exoplanets, because stars give off visible light. That's why it's bright outside here right now. The sun's giving off visible light, and that's why we see invisible light. But planets tend to emit primarily in infrared. Another reason is the very early universe is so redshifted, it's into the infrared also. All that visible light's been shifted into infrared. So the James Webb is optimized for that.
And that's because it's all
Expanding away from us
us?
so fast.
Okay.
The further you look out, as Hubble found, the faster it's receding
So
away.
the light's being stretched. as it
Stretched out,
goes.
so it's what may have been originally blue light is now infrared light because it's stretched out so much. So the James Webb Telescope has been optimized for that. And it should be able to look for atmospheric signatures in these exoplanets. As they pass in front of their parent star, what's going to happen is we will see the starlight passing through the atmosphere and presumably see spectral lines in that. We've done that already for these hot Jupiters. Now, some other telescopes which are going to be coming online about the same time are what we call the next generation just telescopes here on Earth. And these are, just to give you the names of them, one of them is called the TMT, 30-meter telescope, very easy name. Another one is called the ELT, Extremely Large Telescope. And then there's the EELT, the European Extremely Large Telescope, and that one's going to be...
Going back to astronomers, just using simple terms.
Right, simple terms, we're simple-minded people. And that one is going to be, the EELT, European version of it, is going to be 42 meters across. It would barely fit across in Lucas Oil Stadium,
Wow.
to give you an idea. And the structure has to go around that. So you're going to have something roughly the size of Lucas Oil Stadium
Wow.
sitting down in Chile. And that is going to have what we call adaptive optics. It's going to do much better than the James Webb Telescope.
Really?
Yes, and that's the amazing thing. The technology has really helped out here, what we can do looking through our murky atmosphere.
And
So are those still pretty far off in the distance, or is
No,
by the
these are
time the James Webb?
they're talking about James Webb probably, 3 years we're saying, usually multiply that by at least 50%.
Yeah.
It's the time that's given. And even these extremely large Earth-based telescopes, they will be able to do probably just as well or better for exoplanets. In fact, they probably will be able to get spectra of some of these potentially habitable planets. And that's what they're really pushing for, is to build the technology to get that information on those actual planets. In addition, there's a lot of other science too. It's really interesting because the field now has developed, now there's stellar astronomers who work on stars in the sense that they're interested more in what the stars do of various types. Can a red dwarf, for instance, what happens if you have a exoplanet next to that? Does it give off too many solar flares, for instance, because of its magnetic field? And so people are really investigating those aspects of stars, which they've just ignored in the past. But now, because exoplanets have come into play, it's really become, just for stellar astronomers and the planet people themselves, it's really become interesting.
And that's something that I may have discounted in just me being a casual observer interested in astronomy is, a lot of times folks like Sarah Seeger and a few other astronomers that were kind of there from the start talk about how this was really just supposed to be a census.
Right.
And how it's grown to be so much more than, well, let's just see how, let's answer a very basic question of how many planets could we expect on average around a star, to grow to what it is now, where we're talking about alien megastructures around a planet. And so that basic question has been answered, has it not?
Oh,
Just
Mini Neptunes and super Earths are the basic, what we find the most common types of planets.
And the fact that you can expect at least one planet probably around every star.
Every single star you'd expect at least one planet. The estimate right now is at least 200 billion planets in our galaxy, the Milky Way. That's just our galaxy, of any type. And that probably, I'd say, is probably not underestimate. So a curious thing, what you were saying is the stellar census of sorts. It's almost like, if you think about it, it was looking at close to 200,000 stars 24/7. That would be such as the Census Bureau coming into our households and seeing what we're doing 24/7, everyone inside of I-465 for 3.5 years, and developing, I mean, it would actually be an interesting study, a little strange kind of study, but for sociologists to be very important. What do people do during the day and during the night?
Right.
What, maybe you don't want to know.
What
goes on?
that many people,
Astronomers like to
it's
know
on
what goes
TV.
on at night, but not with people, but with stars.
Right.
And the interesting thing was, it was not just about planets. The stellar astronomers were they went berserk over the data.
Oh, really?
Because we had census information 24/7, well, just 3 years straight of data for basically 200,000 stars, which told us about how stars vary in brightness, how they compare to our sun. The sun's the only one we can really observe 24/7 because we have observatories all over the world. So it was really, the Kepler mission is going to be one of those missions that stands out in human history, in my opinion. Like the Apollo missions, there's also ones like the Voyager mission that went to the outer planets in the 80s. Those are the missions that will stand out 50 to 100 years from now. You're contemplating that. Okay. Wow.
Well, and I never really thought about it like that. I mean, because I've kind of followed it just because it's something that I'm interested as a hobby of reading these articles, and I guess that's right. I mean, when you're talking about the dominant news coverage on a regular basis the last 5-10 years, it's definitely been exoplanets, and well, maybe not 10 years, but 5 years it's been.
And certainly people say, well, doesn't this cost money? Yeah, it does cost money. And I like to tell people, I said, well, that's what makes us human. I mean, for instance, what is immediate return to humanity? There is no immediate return. It's just pure curiosity.
Right.
And I try to tell people this, because I've done a lot of things at the observatory where we had groups come in, whether it be, arts or things like that, and they have bring their donors and things like that, and we have events for them. And I made a point to a lot of these people. I said, music is like astronomy, and the arts are like astronomy. What is the immediate feedback? Because we always talk in academics, what's the feedback to business today? What's the feedback? Well, how does this apply to business? I don't really care what the feedback to business is immediately, because there will be payback in this. The technology we're developing to find these things is enormous. And the Kepler spacecraft is like that, in astronomy in general. The public likes astronomy because it basically gets to our curiosity in our exploration as a human species. And that's one thing about Kepler. And just to give you, it costs somewhere in the neighborhood of $1 billion so far. That's the cost of one B-2 bomber.
Right.
And so you don't hear a lot about B-2 bombers, but you hear the Kepler mission all the time and what it's done for us.
Right. And the successor to Kepler is TESS?
There's a number of them that various organizations are putting in, and the acronyms keep changing, so it's hard for me to actually keep up with them nowadays. But the next generation, there's various types going out, some to keep following up on Kepler.
Sure.
But others, there's one that's we're hoping to get in about the next 10 years, if the Earth-based telescopes don't beat the space-based telescopes at this, is really they want to start getting to where they can get not just atmospheric signatures, but spectra from the surface of the planet itself.
Okay.
Because imagine you get this a signature of oxygen-2. Oxygen-2 should not be in an atmosphere unless there's life like we have here on Earth. Now, of course, we're making a big assumption that all life is going to be like here on Earth, assuming it exists out there. Presumably, if it's a terrestrial planet, you'd probably find something about water or carbon dioxide type atmosphere with nitrogen, similar to what we might find on Venus or Mars. But oxygen would be a telltale sign. Or you see some molecule that's strange, like chlorophyll, which you would probably get if you look at the spectra of the Earth, because you would see from the trees we have here. And so you would have some interesting signatures. And I think that's what we're going to be seeing in the next 20 years, is starting to get actual spectra of these planets, which don't expect an image like the Apollo astronauts took of the Earth as they're orbiting the moon, okay?
Right.
That
No direct imaging.
We might see it, some younger people might see it in their lifetime, but the key thing is we have ways of getting information about these planets without even technically making pictures of them.
Sure.
And we always see the artist's rendition, which can be misleading. It looks sort of like Star Wars.
Right. But that would be, a more realistic expectation than what maybe folks have a unrealistic expectation of SETI, of like the movie Contact in the 90s, where
Yeah.
where there, you know, some woman with listening with headphones for an alien signal. A more realistic approach, I think, that some people are making
Right.
predictions.
It's interesting.
in the next 20 years.
Contact was the Jodie Foster character in Contact was actually a real character in real life. It was now I can't remember her name. She's been to Butler twice. Jill Tarter, that's her name, who's recently retired from the SETI program. That's who Jodie Foster's character was modeled after. And it's interesting because Jill Tarter, I chatted with her many times about the movie, and Carl Sagan did a great job with the movie because he made sure it was relatively scientifically correct. Other than building a machine and you don't know how a wormhole's created.
Right.
But he sort of glossed over that, which is why it's science fiction. You can ignore certain facts. But that was an interesting thing about, and it's one of the better, if I say what's a good science fiction movie, I'd say 2001, Space Odyssey. Contact's a great science fiction movie too. Where they actually went to astronomers, it was written by an astronomer, and they got it relatively correct.
And we shouldn't really be expecting maybe signals anytime soon, but definitely at least
Spectroscopy. Or
that comes back
right,
saying,
right.
Yes, there's water,
Yeah.
O2.
Oh, right. O2 would be just, we'd all be going berserk if there was a found O2 on the planet, because that would be such a signature of life. And just to keep in mind how rare that would be, even here on Earth, O2 has only been above the 1% level for about 15% the age of the Earth, the last 15%.
Wow.
And that's since land animals have basically come onto the surface of the Earth, and before that, everything was in the oceans, and that's because we didn't have an ozone layer yet.
Sure. Well, speaking of oceans and water.
Okay. All right.
The other recent discovery was NASA announced a couple weeks ago water on Mars, which I don't think anybody would have 10 years ago or 20 years ago guessed. Well, yeah, maybe there might be ice, but actually flowing water is a whole other story.
The flowing water, that was an interesting one. We knew there were ice caps on Mars. We knew that Mars had water in the past, distant past. We're talking, the solar system's roughly 4.5 billion years old. Big number. Mars appears to have been basically geologically inactive for the last 3.5 billion years. But in that first billion years, it was very Earth-like, not in the sense that it had life, but it had flowing water on its surface, and it probably had seas. From what we found from all the rovers we put on there, images, you see riverbeds. We see it had volcanoes at one time, so it was very Earth-like in that sense. It was probably Earth and Mars were going in tandem at that point. Mars was too small. It's geologically dead now. It's lost a lot of its heat. But what that indicated was, okay, so we shouldn't see liquid water because the atmosphere is too thin. What they found with the Mars Reconnaissance Observer was that there were these on the sides of southerly or northerly facing craters, depending on what hemisphere, the sunlit side of craters, they'd see these gullies developed in the summertime. And what would happen is they'd get dark, like they were soaked in liquid. Just like you throw water on dirt, it appears darker. And they thought, well, it's maybe just perspective, the way the angle of the sun. And some people started to say, maybe it's snowing or something on Mars. Well, we don't see any clouds, really, it's significant clouds. And, I mean, that's the way science works. You throw stuff against the wall. I won't say what you throw against the wall. Some of it is crap, okay? But that's how science works. And you see what sticks. And then what sticks, everyone starts deciphering and trying to pull it apart to see if it sticks even more.
Well, it's what we learned in middle school. You throw out a hypothesis and you test.
Right, and that's what science is. Just because someone throws an idea there, like alien megastructures, that doesn't mean it's going to stick to the wall.
If it would just stick.
Yeah, that would be...
I'm already convinced.
Okay, all right. Well, I would not... You might want to play the lottery then instead if you have those good odds. But anyway, so... they started to do other work and look at the colors. Then sort of a poor man's version of spectroscopy, where they look at more wider color bands to see what was happening. And they realized it was liquid water that was coming out of the sides of the craters, almost like permafrost melting when the sunlight would hit it. And then it would melt, even though it was below the freezing point. The thing is, it's very, very salty water, which means it can't exist at a liquid below 32 degrees Fahrenheit. And so they realized that's what this is. And so it was really interesting in that case. Yes, there is liquid water in a temporary state on Mars. You see it coming out of the sides of craters and
Sure.
as far as the permafrost melting, it's very saline, and then it comes out, and then it basically just quickly evaporates into the atmosphere. So Mars does have some of that. And that's useful, the fact that we know there is water below the surface, because if you send people to Mars sometime soon or distant future, they will actually have to have water to survive. You can't bring it with you. And that's the key thing, why water is a key resource for traveling to Mars.
And the saltiness of this water likely may be useful to any human mission, but not suitable for life.
Well, then again, I mean, it is very salty. That is one thing about it. It's much saltier than our oceans, okay? But life has a weird way of
Finding a
here
way.
on Earth. We have it at volcanic vents under the oceans where the energy source is not sunlight, it's the warmth from the vent itself. They're told almost fully, not quite fully enclosed, but just their own ecosystems. And so you could have presumably something like this too. I mean, we've sent probes into space and brought them back, and we find the microbes still on them, living. So if life's anything like it is here on Earth, I wouldn't be surprised if let's just imagine we're the only life in the universe. Well, I suspect we're spreading life already onto Mars, perhaps.
Right, and that actually was one article I read, was that they won't send the rover or any. I guess there's 2 rovers that are still working on Mars, and they won't send any. One I think is probably too far away, but the other they would never send it anywhere near there because they don't want to contaminate.
Right. We don't want to contaminate anything, and because we want to actually go there and see it somehow, whether it's humans or get a sample, and to try to sterilize a rover is very, very hard. Because it's going to be sitting on the launch pad, whether it's at Kennedy Space Center or Vandenberg Air Force Base.
There's no way to confirm.
Yeah, I mean, even if you can't vacuum seal it, and then undo it when it gets there, it's very hard to do to not to get any microbes on it.
Well, I guess the last topic that I have
Certainly.
for today is just for fun, because tomorrow, October 21st, 2015, is the day that we should all be expecting Marty McFly to show up, which is obviously referenced Back to Future Part 2. And so I think an always fun topic of conversation is time travel and whether anything like that would be possible.
Well, we've actually sort of touched on part of it already with Contact.
Okay.
Contact was not time travel, but time and space are intertwined with each other. And in Contact, Jodie Foster, went through this wormhole. But from here on Earth, the people at wherever it was, Kennedy or Japan, I forget, they thought she was only, just watched a drop, and it was 8 seconds, and nothing happened. Where in reality, she thought she was gone for 18 hours. And that's something we call general relativity, which Albert Einstein figured out. The warping of space due to mass, and traveling at various high speeds, you can slow down time. Now, going backwards in time, we're cutting a hole through space versus a wormhole, and things punching holes through space to get somewhere quickly. Time travel is one thing that is much harder to try to perceive, particularly going backwards in time. And many people have worked on this, particularly in the 1990s. I mean, we're talking true theoretical papers, particularly out of Caltech, and some of them were, Stephen Hawking has discussed this too. But the Caltech people, Kip Thorne in particular, and his graduate student Mike Morris, who worked on the physics for Contact for Carl Sagan, they also considered time travel. And their conclusions were somewhat, maybe, but we're not sure. They said, yeah, if you're given infinite resources, you can punch a hole through space and end up on the other side of the universe.
Yeah.
And you can do it very quickly if need be, and not, and slow down time. But as far as going backwards, that's the harder one to do.
And that was going to be my question, if there was a serious question in there somewhere in regards to Back to the Future, was it seems like the part 2 where they go to the future is really the only one out of the three movies that is actually possible, because if Marty is traveling at a high rate of speed, the closer you get to the speed of light, he perceives
Slowing
time
down,
as
right.
slow, and
right,
everyone
right.
else is speeding
that,
up.
That
so-
way, and that's a reasonable assumption. That's what we call special relativity, where you're just moving fast. General relativity has to do with warping of space. But that's exactly.
But I don't think
But
88.
his doppelganger in the future wouldn't be there. It would just be him as the 1985
No, his
guy.
doppelganger could be there, and that's sort of a paradox that everyone's sort of like, well, what happens if you meet your doppelganger?
Yeah.
I mean, we have all these certain paradoxes in science. Like,
But 88 miles an hour would not have been fast.
not fast
No,
enough.
no, that's
He
not
would have
even
needed
close.
to be closer to the speed of
right,
light.
right. The interesting, I think Mr. Fusion is much more likely than time travel. Okay, if you remember Mr. Fusion
Yeah.
on the back of a
Yeah.
DeLorean, so that's probably more likely in the near future than time travel.
At least clean energy. Yeah. That
Yeah,
would be
yeah,
great.
yeah. That would be great. So.
Not if the oil companies have anything to say about it.
And on that note, anything coming up soon at the Holcomb Observatory?
We are actually, we always have, not always, but generally when we're in session at Butler and we have students around, we have planetarium shows every Friday and Saturday night for the public.
Oh, cool.
And we have telescope observing. Our big telescope is undergoing a $500,000 renovation right now. And we're hoping to have it going through testing here within a month. And that's going to be one spectacular instrument because if all by itself, it's close to a $2 to $3 million instrument.
Wow.
It's one of the more expensive scientific pieces of apparatus in this city. And some of the views you get of planets are just absolutely spectacular. There's nothing like, when you tell people, you're looking at Saturn, and what has happened is photons have traveled from the sun, which have been formed by nuclear fusion, reflected off the molecules in the atmosphere of Saturn, and come back, reflected off the mirror in the telescope, and hit the back of your eye to produce a signal.
That's awesome.
I mean, or you can point at the Andromeda Galaxy. These are stars that emitted the light 2.5 million years ago, and those photons have traveled 2.5 million years to reach your eye. So it really is an amazing thing when you do look through a telescope, and I highly recommend people come out.
Very cool. Very cool. Well, Mark, anything you're looking forward to in the near future?
Nothing.
Well, I think
I'm sorry for that. Okay.
Just day by day, man.
just day by day. Well, as I've mentioned, I think before, this week and continuing into next week, I think the Heartland Film Festival is going on, so check that out. But otherwise, as we always try to plug for Liberty Street, they've got their events going on here all the time. At least tonight, they've got a open mic night.
$4 pints.
$4 pints.
Just can't plug that
Tuesdays,
enough.
right? Can't give them enough publicity for that. So anyway, thanks a lot for listening, everyone. Hopefully you'll come back next week.
My eyes better pray for peace. God my kin, 'cause the thunderhead is rolling.